Hello everyone. So in today's video, I'm going to go over this paper titled Determining Code Words in Euphemistic Hate Speech Using Word Embedding Networks. So this paper is by Rijul Magu and Shebe Lu from the University of Rochester. The abstract. While analysis of online explicit abusive language detection has lately seen an ever increasing focus, implicit abuse detection remains a largely unexplored space. We carry out a study on a subcategory of implicit hate, which is euphemistic hate speech. We propose a method to assist in identifying unknown euphemisms or code words given a set of harmful tweets containing a known code word. Our approach leverages word embeddings and network analysis through centrality measures and community detection in a manner that can be generalized to identify euphemisms across contexts, not just hate speech. Alright. So this is a continuation to the previous paper, which was more oriented towards showcasing that these code words exist. Now the and the future works which they mentioned in that paper included automating the process of identifying which words are acting as code words, and that is what they're trying to accomplish in this paper. So, introduction. Euphemisms as an instrument to mask intent have long been used throughout history. For example, a rich lexicon of drug slang has developed over time, with entire communities subscribing to benign sounding words that allude to names of drugs, intake practices, or other stakeholders such as dealers. In these instances, the primary motive is often to get a message across while evading detection from authorities. The main obstacle in these cases is the inability to identify code words without gaining access to an explicit mapping between the words and their latent meanings. Often, these words are already embedded in such common parlance that they cannot be spotted without placing the correct context. So I guess this is pretty self-explanatory. We've seen this in movies and other places as well. People using some other word to disguise some other intent. Notably, in 2016, a number of users across social media platforms and internet forums, particularly 4chan, began a movement called Operation Google, a direct retaliation to Google announcing the creation of tools for the automated moderation of toxic content. Essentially, the idea was to create code words for communities within the context of hate speech so that they would not be detected by such systems. The movement branched out to a number of social media platforms and, in particular, Twitter. The complete list of all code words is presented in Table 1. So you can see these words are being used for these actual words. Recent work has begun to emerge on studying this instance of euphemistic hate speech. However, they largely deal with the impact of code words in hate speech. Our work instead focuses on moving towards automating the discovery of code words. The objective is to significantly decrease or even eliminate the need for human effort required in manually evaluating what words could be euphemisms. That said, the solution and processes we describe go beyond finding use within the hate speech context. While some parts of the pre processing stages do benefit from being aware about hate speech associated issues, the fundamental approach is general enough to be applied to assist in extracting code words in any context that may be found in natural language. So, though their work is benefiting hate speech as well, hate speech identification, the technique which they've developed can be used to identify code words in any form of language. Additionally, our technique revolving around studying the structures of the word coherence networks that emerge from instances of coded hate speech also lies within a predominantly unexplored space. We find that the centralities of word nodes within such networks indirectly provides crucial hints about the context within which they arise. Alright. So the abusive language section. The past few years have witnessed an increased focus on abusive language, particularly hate speech detection, with a variety of different approaches and applications to a diverse set of contexts. These have ranged from classification of hateful tweets using bag of words and type dependencies to using semantic structure of sentences to the study of targets of hate. Others have used related methods to study phenomena closely associated to hate speech, such as cyberbullying and offensive language in general. From an application perspective, Magu et al. Create models to predict the extent of harmful content in the comment section of news sources using titles and body information as input, indicating a relationship between the entities. So this seems pretty interesting. I would like to check this paper out because just using the article title and body information, you're sort of trying to predict whether the article is uh, racy enough or something the article deals with is inflammatory or something which challenges the beliefs of certain peoples that would prompt them to write harmful stuff in the comment section. Davidson et al. A recent work on hate speech detection notes the difference between hate speech and offensive language. Notably, Wasim et al. Provides a typology of abusive language, categorizing abusive language across two dimensions. One, the target of abuse, and two, the degree of abuse being explicit. In terms of target, they distinguish directed hate, so hatred towards an individual, like go kill yourself, and generalized hate, hatred towards a recognized group. For so this example. With regards to this, a number of studies have been carried out that measure and study this effect, particularly within the context of social media. For instance, El Sharif et al. Deal with analyzing the characteristics of hate speech instigators and targets on Twitter. For the second dimension, the authors differentiate between explicit, containing language that is unambiguous in its potential to be abusive. Examples could be language containing racial slurs, and implicit, containing language that does not imply or denote abuse. For example, this. The authors discuss the role of context which is needed to correctly identify hate. As such, they touch upon the fundamental mode of expression that displays implicit hate, which is euphemistic hate speech. Euphemistic hate speech stands separate from other forms of implicit hate speech, namely microaggressions, because in truth they are often direct toxic attacks as opposed to veiled or context dependent ones. So more often than not, like if you see some recent works from the 2020s or 21s about implicit hate speech, you'll see that a lot of stuff which they're dealing with seems to be just masking the intent behind words. So it might be sarcastic, or it is not really openly saying what it wants to say. It's just putting it out there, and people just uh, guess the implied meaning themselves because they're already they've already seen other tweets by the user, or they know the beliefs of the user, or they share similar beliefs to the user. They are implicit because they make use of clever word substitutions in language to avoid detection. Even a classifier trained on a hate speech dataset containing instances of code words can fail to identify hateful content if new code words, either intentionally or otherwise, start being used by the community. Indeed, currently the only available option to recognize such instances manually, which is often inefficient and burdensome. Therefore, this motivates the exploration of more automated methods to detect euphemisms within the hateful context. So 2.1 is euphemistic hate speech. To clearly define the problem of euphemistic hate speech, we start by looking at the general definition of hate speech as given by Davidson et al. They define hate speech as language that is used to express hatred towards a targeted group or is intended to be derogatory, to humiliate, or to insult the members of the group. In this sense, we note that euphemistic offensive language also qualifies as hate speech because it targets communities based on race, religion, and sexual orientation. As a result, hate speech that relies on intentional word substitutions to evade detection can be considered as euphemistic hate speech. So, this is like the very basic definition. As discussed earlier, one of the most prominent use of euphemistic hate speech came as a result of Operation Google ever since the movement started in 2016. For instance, Hein et al. Studied the usage patterns and behavior of a community on 4chan and Twitter. Finally, Mavo et al. Analyzed euphemistic hate speech on Twitter, creating a tool to automate the process of segregating tweets containing code words from those containing code words but that are benign in nature. So the code words are generally words which are used in the wild pretty often. So you also need to be able to distinguish between people who are using these code words intentionally and people who are using these code words in their real sense. Alright, so the dataset, we collected approximately 200,000 English tweets containing the code words using the Twitter streaming API. The time range was crucial for us as we wanted to study the use of code words as they propped up. Therefore, our extracted tweets were concentrated between September 2016, when the code first gained prominence, up until November 2016, slightly after the election season in the USA. Next, we need to select a single code word that could be used as a starting seed word for our analysis. Effectively, the aim was to retrieve other code words knowing only one code word beforehand. So they chose the code word Skypes, which is used in place of juice. and manually extracted 850 random tweets that used it in hateful content. So you can see some examples. From this point on, of both what are and what are not hate speeches. From this point on, all our analysis is carried out on the dataset of hate speeches containing the word Skype. Note that the set of tweets can do contain other code words also. So you can see they're using multiple code words here. As a proof of concept, we showcase the entire process starting with Skypes, but this can be extended to other starting codes as well. While we recognize the value of a comprehensive study of the methodology across the entire spectrum of combinations, retrieving all of the codes given any randomly selected initial word, it went beyond the exploratory nature of our work. Alright, so they're just saying that they did not deal with that work because they already are covering a lot of stuff in this paper. Importantly, as an artifact of the time range of the data, we do not expect there to be any previously unidentified code words, or at least not once used extensively by the community during that time within the dataset, because this is the time when Operation Google started. Therefore, to validate the working of our methodology from this point on, we instead assume we have no knowledge of the existence of any other code word besides Skype. Indeed, our method does not incorporate or exploit any hints it may derive from knowing any of the code words beforehand. So they only know that the word Skype is a code word, and they're using that as a starting point for the rest of the work which they're going to do. Alright, so the baseline. To assess how well our method performed, we needed to establish a baseline method. Currently, the simplest way to identify code words in natural language would be to manually sift through a series of tweets of users belonging to known hate communities. Clearly, this is arduous and ineffective. A reasonable approach is to rank all the words in a corpus on the basis of some metric so that the higher ranked words have a greater chance of being code words than the lower ones on the list. For a small time frame like ours and without any prior information, a good bet would be to use word frequency as the metric. Note, there might not be any qualifying indicators for a specific word to be a code word. Right? This is based on the idea that rarely used words would be unlikely candidates for code words. This also makes sense at some level, because if they are used, then they wouldn't use words which would gather suspicion, right? This method forms our baseline. As a result, the base ranks of our code words were the ranks of the words on this baseline list. Thus, we can quantify the performance of the method we develop by evaluating the rank improvement of code words against the base ranks. The base rank is just the frequency of words. So you can see this is the baseline frequency in their dataset. Alright, so the pre-processing, we made use of a strong, we made yeah, we made use of a set of strong assumptions about hate code used in natural language to inform our data processing decisions, visualized through Figure 1. It is worth considering that these as assumptions help immensely in narrowing the space of possibilities. They are general enough to be applied to any scenario involving coded speech. Additionally, it is important to note that the numbering of these assumptions does not indicate a sequential order of processing in terms of trimming down words. This is because some of the steps benefit from having the entire unaltered tweet available to them. Pruning is carried out after determinations are made for each word through all of the assumption steps. These assumptions are as follows. So assumption 1 is that the code words are nouns. Assumption 2 that they are not words normally considered negative. And assumption 3, they are not either extremely generic nor are they very specific. So all three assumptions are pretty fair, I believe. And so this is the figure which they've depicted. So let's have a look at the figure itself. uh, I think I just need to reframe it a bit. Right. So you can see you have the clean tweets, you extract the nouns, you lematize it, you remove negative words, and then you remove too generic, too specific, or words directly related to Skypes. So all of this is uh, based on the assumptions that they made. So it is safe to assume that the words would be nouns uh, in the context they are written within tweets. It is to be noted that all code words are used in place of references to real communities, which in turn are necessarily nouns. As a result, although the references themselves are replaced, the syntactic structure themselves of the tweet remains intact. Hence, the code words like the communities themselves would be detected as nouns by syntactic parsing. Therefore, we use pause tagging to extract the set of all nouns from the list of word tokens. Next, we lemmatize these tokens to bring them to their base forms. This is of critical importance because we would like to construct a network at some point, and without standardization, we would be left with multiple duplicate nodes and unclear results. So this is also pretty self-explanatory. For instance, you might have like 10 different variations of the same word, then you'll have a lot of duplicacy and redundancy in your network. Additionally, carrying out lemmatization at this stage considerably reduces the space of possibilities early on, allowing for faster computation during later stages. We move on to our next assumption A2, namely, code words are not words normally considered negative. Using using words that are already negative, for example, this defeats the purpose of using code words to begin with. Aside from immensely confusing readers, for instance, replacing these words in the new sentence, even if terrorist has been adopted as a code word, it would become impossible for the author to convey whether they meant killing some other community. Hence, we attempt to remove all negative words at this stage. We do this by importing the list of negative words assembled by Hu and Liu and removing words from a lemmatized set that match those in this list. I'll be right back. Hi, sorry about that. There was someone in the door. Alright. So the third assumption, A3, they are not either extremely specific nor are they very generic, is checked for next. Clearly, like in the previous case, it is very confusing if the code words are too broad. For example, uh, these people are disgusting, these men are disgusting, something is disgusting. All of these have alternate meanings as well that fit well within the context but are too generic to be used as code words. As a result, we discard these. Similarly, using specific words is also uh, using referring to individuals or the community itself makes it too specific. Therefore, you cannot assume that they are acting as code words. So the assumption is that two generic and two specific words are not code words. Therefore, we use a mix of named entity recognition and manual pruning to remove these tokens. Next, it is imperative to also exclude words that are directly related to the known code word. For example, if we need to remove instances like Jew, gas, Holocaust, etc., when using the dataset for Skypes because they already exist within the context of anti-Semitic hate speech and cannot be used as code words by definition. So the definition of code words was that they are euphemistic and they are replacing some sort of indicator. They're replacing the real intent. Yet they may affect our analysis because of their yet they may affect our analysis because of their expectedly high common usage. This is the only part of the filtering process that requires some basic knowledge of the problem. As our final step, we discard the word Skypes itself, since it occurs in every single tweet and provides no additional information. So this part is very interesting because up until this point, nothing required information related to task. But as you can see, this choice depends on the initial starting word. But I guess this is also a reasonable choice because you cannot do everything zero shot, right? You need some information at least. Alright, so detecting euphemistic hate speech. The main idea behind how our system works is that code words are an abnormality within the context defined by hateful users. So words like Google, Skype, Yahoo, etc. are not expected to occur regularly in tweets aiming to attack groups. For example, the occurrence of Skypes and Googles is an aberration with respect to the surrounding words within the following. Uh, I didn't really get this. Let me just read this again. The main idea behind how our system works is that code words are an abnormality within the context defined by hateful users. So words like Google, Skype, Yahoo, etc. are not expected to occur regularly in tweets aiming to attack groups. Right. So this is a fair point. For example, the occurrence of Skype, Google is an aberration with respect to the following surrounding words. So you don't expect these surrounding words with these words. So that is why these also act as code words, because if you expect them to occur, then the main idea of conveying a different meaning would not work. Alright. So news data word embeddings. As a result, we can exploit this effect by representing all our word tokens by their word embeddings that have been pre-trained on a regular, not necessarily hateful context, and evaluating how dissimilar they are with respect to each other. So they use Word2Vec from Mikolov et al. Embeddings trained on a Google News dataset built on Google News articles with over 100 million words and find a pairwise cosine distance for all words. Essentially, we expect the code words to be further apart than other words which belong to the hate speech context. A subgraph which is with a few representative nodes can be seen here. So you can see Google and Yahoo, and you can see all these other words as well. So the red nodes are code words, whereas the yellow are non-code words. The diagram is for representation only, and these labels are not provided beforehand. Right. So the primary limitation to this approach is that some of the code words do not have representation within the pre-trained model and might be missing entirely. So these words. So why this? So since Word2Vec is trained on uh, it's a 2013 model trained on the Google News articles curated before that. Then words which popped up before that, after that, are words which did not show up in the dataset do not have a vector representation. The hate network. Since pairwise relationships between words are now quantified and these relationships cannot be assumed to be independent of each other, an intuitive way to study the structure would be to model it as a network. The degree separation is graphically represented in figure 4. Specifically, we created a network where each node represented a particular word and the edges denoted a cosine distance between the respective word embeddings. In addition, we decided to leverage the fact that a sizable number of words did not co-occur together in tweets. In addition, we decided to leverage the fact that a sizable number of words did not co-occur together in tweets, thus providing us with additional information about context. So this is pretty intuitive, I guess, because if you have say 10,000 words, you won't expect every word to have occurred a lot of times with every other word. As a result, we prune all edges where the connected words do not ever occur together in any tweet. So even though you might have some similarity measure, because you can always do a cosine distance between two vectors, if they never occur together, then there's no point having an edge between them. Some characteristics of the graph, such as number of edges and average degree, are given in table 3. Alright, so you can see the graph. Nodes are colored by the connected components they belong to. Those belonging to components insignificant in size are colored gray. The giant component is colored orange, and the size of nodes corresponding to degree. Also, the size of the nodes corresponds to the degree. The largest node in the center is Google. So this just means that this the larger node, the more things it is connected to. So these are just a different set of connected components and so on. Also, this is a degree distribution and log bin degree distribution. So you can see what the degree is and what the log bin degree distribution of this entire network looks like. So these are just terms used in network analysis. The network displays characteristic typical of a complex network. For instance, the network shows the small world effect. We evaluate the value of the cluster coefficient and the mean shortest length path for the network, and then find the average of those metrics across an ensemble of 100 random graphs with the same degree distribution. This allowed us to calculate the value of the small world coefficient, which is found using equation 1. The value was noted to be 20.46, which is much required than the threshold of 1 for a graph to show the small world effect. For a graph to be expected to show the small world effect. So you can see you have 1129 nodes, 2188 edges, the average degree is 3.88. You have the clustering coefficient and the mean shortest path length. So this graph is showing the small world effect. Word ranks. As noted by Mabo et al. 2017, the code words tend to extensively co-occur with each other. There are a number of possible explanations for this effect. First, as people warm up to a new code, they are incentivized to use as many different words as possible so that the code gains traction among their followers. Using too few code words within tweets could lead to those tweets being overlooked or treated as mistakes. Second, the alt-right, the primary users of code, tend to display blanket hate towards a number of different communities across the spectrum of race, religion, and sexuality. Therefore, the tweets often simultaneously target a number of different groups, a pattern which in turn is replicated in their code word usage. In this circumstance, we decide to use eigenvector centralities words as our ranking metric. Eigenvector centrality estimate techniques attribute higher centrality values to nodes that are connected to other important nodes. This was very relevant to our context since we know that the existence of certain words which are hard to predetermine within hate speech have an effect on whether surrounding words could be code words or not. The ranking of code words are shown in table 4. As you can see, all code words barring those without word embedding substantially move up the ranking order when compared to the baseline model with a mean jump of 134 positions. Interestingly, the improvement for butterfly was not as dramatic in terms of its final rank, likely because it might have co-occurred with words considerably different than those connected to other code words. So this is the improvement improvement over baseline, and this is the centrality rank, the eigenvector centrality rank. So note that centrality values are improvements for some words is absent because they did not have a word embedding in the word to vec model. So you can see this is already much better than the baseline. The candidate cluster. There is one major issue with the above discussed approach. Manually moving down a rank list to discover code words can be cubism. Additionally, there is no bound or limit till which we can expect to cover all or most code words. Therefore, perhaps a more useful technique would be to suggest a group, a cluster of candidate words which have a high chance of being code words. Community detection analysis on the network is hence a viable approach. First, since the graph is connected, we focus on the largest component or the giant component of the graph to carry further analysis. Since we know that the code words are likely to be closely connected to each other, we expect to find cliques, which are sets of completely connected subgraphs within the network. Therefore, we applied the click percolation method on our graph to achieve overlapping communities of words. Essentially, the click percolation method works by constructing communities from k clicks, where k is a natural number. A community is obtained by finding the maximal union of k clicks that are within reach from each other through a sequence of adjacent k clicks. Here, adjacent k-clicks are those clicks that have k minus 1 nodes in common. Since we do not know the optimal value of k, we carried out a separate analysis for each value of k starting from 4 to 8, which is the largest possible value such that no k plus 1 clicks exist in the graph. Judging by the extremely high clustering coefficient of the graph, there are an immensely large number of triangles in the graph. As a result, the algorithm is non-trivially affected because essentially all or most nodes are grouped together into a single community. That is why value of k less than 4 were not considered. Alright. Next, we need to find the optimal community out of the following possible communities we have achieved for each value of k. A common approach is to simply select the largest community, which implies a community with the most number of nodes. This approach assumes each node to have the same weight. However, since we know that eigenvector centrality serve as a useful indicator to finding code words, we can weigh each node by its eigenvector centrality. As a result, in place of simply finding the community with the highest length, we summed over the eigenvector centralities of all nodes in every community and returned the one with the highest value. The resulting community was this list. The cluster is you can see lots of words which are the code words. The cluster is extremely tight, consisting of only 10 members, yet it contains all the code words that are present within the word-to-vec pre-trained model except Pepe and Butterfly, with only a few outliers. With some of these, while some of these are likely noise, the occurrence of terms like commie is explainable. The left is frequently targeted by the alt-right, the most common users of the euphemisms. Therefore, these users seem to often group commies or communists together with other targeted communities which have euphemisms within their tweets. This is why they form part of the clique that was uncovered through our analysis. So you can see they are using code words and the word commies. Thus, other than providing us with a set of strong candidates for euphemisms, this approach also reveals useful information about the posting pattern of the community of hateful users. Alright, so they also have some limitations. There are some limitations that we would like to work on in the future. The major drawback is that we need one starting seed code word to find others. We would like to be able to identify seed code words in a manner that we require no prior information about any code words, even at the cost of robustness. Second, it would be useful if we could iteratively improve our performance. For example, if we were able to identify second code word using our technique, the suggestion for the next candidate should adapt appropriately to generate better results. Finally, we wish to achieve the word embeddings on larger varied datasets so that when they're used to find cosine distance, some important words are not automatically missed out on. So all of these are fair and reasonable limitations, which we've explained. The conclusion: we discussed the problem of euphemistic hate speech and now how we can train and challenge, how we can transform the challenge of finding unknown code words into a network science problem. We present insights that can be derived from the pre-processing stage, such as the code words being noun and neither too generic nor too specific. Finally, we show how by using cosine distances between word embeddings could be coupled with analyzing the structure of resulting network to achieve likely candidate for code words. Our approach can be used to detect code words not only within the context of hate speech, but anywhere else where a community may feel the need to use euphemisms within natural language. So the paper was pretty interesting, and this figure, I missed this figure, so I'm just going over that. You have the graph, you find the eigenvector centrality, you also find the k clicks, and then you use both of them, use the eigenvector centralities as the weights to find the optimum community cluster. So overall, this paper was pretty great. This was the first paper which I've covered, which also incorporates network analysis. So hope you guys enjoyed this video and hope to see you again next time as well.